All right. Good evening, everyone. Tony, are you checking this out on YouTube? Make sure it's coming through. I think it should be fine. Thank you. Thanks everyone for bearing with me last week as I laid in bed and collected my first samples for that study. Talking around, apparently a lot of people were sick last week. It's sort of, I guess, early peak of the cold and flu season, and apparently, as I learned from Tony, I was sick at the same time last year. Okay, sounds good, great. But I'm back. Hopefully, the last time I'll be sick this semester. And while you covered confidence intervals with my ghost last time, we're going to review it a little bit today and move on to hypothesis testing and the relationship between confidence intervals and hypothesis testing, which we will do for a single population mean and a population proportion. We'll go through a bunch of steps of hypothesis testing to formalize it, writing out the null and alternative hypotheses in a formal way, and defining type 1 and type 2 error. I wish I could remember how to turn off the volume in the room, but I don't, so we'll live with that. So as you covered last week with the video, confidence intervals have an interpretation that is actually not. What's that? Oh, you lost.
Yeah, I don't see it online.
You don't see it?
No.
Let's see. What do you see?
I see the previous session, session 5, 4, and 3, and so on. I don't see. We don't have 6 because that one's.
It says we're live, so
I'm not seeing it displayed in the on the what do you call it, on your subscription page. Maybe you can send. Not seeing it displayed in the on the not the what do you call it, on your subscription page.
Can you see it?
Maybe you can
see it
not seeing it displayed in the on the what do you call it, on your
we have some people
on your subscription page.
Can you see it?
Maybe you can see not seeing it displayed in the on the what do you call it, on your
we have some people
on your subscription page.
Can you see it?
Maybe you can see not seeing it displayed in the on the what do you call it, on your subscription page.
Can you see it?
Maybe you can see not seeing it displayed in the on the on your subscription page. Maybe you can see not only displayed in the on the
central value
on your subscription page. Maybe you can see not only displayed in the
population central value
on your
associated level also
maybe you can see not only displayed in the
population central value which is associated level
maybe you can see not only displayed in the
provides to you range central value which is associated level
maybe you can see not only displayed in the
population what the population oh, that's okay. This should be better. I think I just fixed that problem. Online folks, can you let me know if this is better? Sounds like dying cats.
Much better.
Okay. Okay, so is that clear? The population mean is what it is. The confidence interval reflects our uncertainty in what it is. Much in the same way that my age is what it is. I have no uncertainty about what it is, but if you don't know what it is, you have some uncertainty. You might place a confidence interval around it to reflect how sure you are that my true age lies within that range. That's why I use that example. Yes.
So it's clear to me like the confidence intervals for the population mean.
Mm-hmm.
But I was having some difficulty understanding like how the same concept of the confidence interval for something like the proportion.
Right.
For the binary, yeah. For like how does it work conceptually with that? Or
okay, so how does a confidence interval around a proportion work? For example, let's say the prevalence of the disease in a country where we have a limited surveillance system, and instead of having something comprehensive where we would know that for every case that exists, we know that they would come to a clinic and that would get reported to a centralized reporting system and we would know what the prevalence is. If we were to go to a country where this disease is not generally reported, as for example, cold and flu in the United States, we don't actually know what the prevalence of cold and flu is. There is surely some prevalence in a given year. Some percentage of the population gets the cold or flu, but we don't know what it is. So one approach that you could take would be to take a sample of the population, such as the NHANES study, National Health and Nutrition Examinations study. Take a representative sample of the population and find out whether that sample, how many of them had the cold or the flu that year. You get an estimate. Let's say that 60% of them had cold or flu. Complex survey weighting aside, that 60% is our best estimate of the proportion in the population who get cold and flu. But we don't really think that it's going to be exactly reflective of the prevalence in the population because we only took a sample. And so because it's a sample, if we took another sample of the same size, we would observe a somewhat different proportion. And under either the exact binary distribution for Bernoulli trials, or using the normal approximation, we can calculate what the sampling variability in that proportion would be for the sample size that we have, and based on that, construct a confidence interval for the proportion of people who had the cold or flu in the year that we sampled. Does that make it a little bit more clear? It's the same idea. It just instead of taking a continuous measurement and calculating the mean, you're taking a bunch of yeses and nos and calculating a proportion. But that proportion has is subject to sampling variation in just the same way that the mean is. In fact, you could think if you take your no, I didn't get a cold this year as a 0 and yes as a 1, then it is the mean of those 0s and 1s, and you can then think about it in a very similar way. It's just the mean of whether people had the cold or not.
So it would look similar in terms of like the curves we were showing for the population versus the sampling proportion.
That's right. The sampling distribution of the proportions, as long as it is something greater than an expected number of 5, or what was the rule of thumb that I taught you? As long as it's into the range where that normal approximation holds, that if you took a bunch of samples and plotted those proportions, it would look like a normal distribution with a standard error approximated by that formula that you have. Good question. Okay, so let's look at this. Let's look at this fun survey that had these few questions here. Oops, the formatting got a little messed up here. But I asked of you, only about half of you answered. I was a little bit disappointed in that, but it's okay. To guess my age, to guess Tony's age, and to put 50% confidence intervals and 95% confidence intervals around both. Now these are obviously different than the confidence intervals that you learned about last class, only in that they're not calculated based on a sample. They're just calculated on your own understanding of your own uncertainty. But it's the same idea. It's the same idea of making a best guess and then putting an interval around that for a given level of confidence. Here's what your guesses look like. And these are from your actual survey. What I've done here is to plot the ages along the x-axis and just stack them up by guesser ID, and I ranked them in order of the lowest age to the greatest age. So the lowest guess is about 52 years old, and the highest guess is about 63 years old. And then I put lines so that point guess is the dot here, and then I've put the lines. The red dashed line is the 50% confidence interval, and the solid line is the 95% confidence interval. So, does anyone recognize their guess in here? Do you remember what you guessed? Good. They're all in here. There are two that are identical here, which is surprising. I wonder if that was the same person filling out the survey twice. I noticed that that's the only one like that. But I'm going to go through some of these and ask for your impressions on them. Maybe to start out, what I'd like is for someone to look on here and find one set that doesn't make sense to them and tell me why it doesn't make sense to you. And you can feel free to say that about your own if you think so now, but otherwise, yes?
The second from the bottom.
Second from the bottom, okay, this one down here. Why doesn't that make sense?
Their estimate was not in their 95% confidence interval.
Yeah, their estimate was not within the 95% confidence interval. So why doesn't that make sense?
It should always be within confidence interval because they think that value is in that confidence interval.
Yeah, like if your best guess is here at 51 years old, why wouldn't your confidence interval of your best guesses include your best guess? Yeah, that's a good point. Did you have one too? Same one. Another one?
For the last one, the 50% confidence interval should be, wait. No, never mind. No, but the 95% confidence interval is also not within the point.
Yeah, so here the 95% confidence interval does not include the best guess. There's something else strange about that one too. Yeah? Yeah.
Should the 95% confidence interval be like larger? Or
Yes.
instead of the 50%, you'll know, you'll be more confident in 95% versus.
Yeah, why?
Because there's more, I don't know if I'm saying correctly, but spread in terms of the interval is larger as 95% versus.
Yeah, the interval is larger. I could explain why. Maybe can I get another opinion on why that is before I give my 2 cents? Yeah?
If you want to increase the chances that an interval has the true value in it, you're just going to have to increase the range of that interval.
Yeah, you don't have any more information. So if you want to increase your confidence, you have to increase the interval. You can't say, I'm 95% sure that you are 51 years old, but about 50-50 that you're between 40 and 60 years old. Like, you know, if I extend that interval to between 5 years old and 100 years old, then I'm going to be 100% confident. So generally, the wider a range you give yourself, the more confident you can be in that, right? I think this is actually a common source of confusion in confidence intervals, because the sort of countervailing unintuitive thought is that, well, if you're more confident, shouldn't you have a smaller interval, right? Which is a different meaning of the word confidence than we're using here. So that would be talking about information. If you have more information, then your interval could be smaller. Like if Tony gave you a clue and said, okay, I don't know, can you give us some kind of a clue?
Well, I've often talked about the 60s, put it that way.
Okay, so he's often talked about the 60s. He was alive in the 60s. There's a piece of information that would allow us to shrink our confidence interval, but that's because we have new information. So the same level of confidence, you could then maybe shrink that some based on the new information. But in general, there's going to be, for a fixed amount of information, there's a trade-off between the level of confidence and the size of the interval. The more confident you want to be, the larger you have to, the more margin of error you have to give yourself. Does that make good sense? Are there any others on here that aren't quite right? I think there are a couple more. Yeah?
The one at the top, she said, was the same as the one below.
Yeah.
The confidence intervals are about the same.
Right here, the confidence intervals are about the same. Yeah, there's not a big difference between these confidence intervals. That's actually true in general for these, and I plotted that on the next one to look at it, that there's not a lot of difference between these 50 and 95% confidence intervals. Yeah?
The fourth one down, or wait, no, the fifth one down.
Fifth one down, yeah.
You can't be 95%. Your 50% confidence interval should be inside of your 95% confidence.
Yes. So your 50% confidence interval absolutely should be contained within your 95% confidence interval, which on this one is not the case. Anytime that you calculate the confidence intervals here, it's going to be at a point estimate plus or minus the margin of error, so that the point estimate is in the middle. There are very particular cases where that might not be true, where you would actually have something like this. If you know that from some information that Tony's age cannot be greater than 60, but your uncertainty only lies in one direction, but 60 were your point estimate, there are theoretically ways that you could end up with something like this, where your confidence interval ends at your best point estimate. But that's a weird case. I don't think it would come up in a sample. Might come up in some other kind of a probability thing, but it is weird. I don't know. This one is missing the 50%, but I think you all get the point now about, you know, the main things. Your best guess has to be somewhere within your interval, and the larger your interval is, the more confidence you can have in it.
So the fourth one up from the bottom is just like a really, really wide.
Yeah, it's just a really, really wide interval. This is someone who does not consider themselves to be a good guesser. To be 95% sure they want to guess between 30 and 80 years old. And yeah, to be 50% sure between 43 and 63. Thanks for being our guinea pig here, Tony. Any other questions, comments about this? I will continue using these data in hypothesis testing, so it's not your last chance to talk about it. Oh yeah, and as I promised, I did this calculation also of what the actual ratio is between a 50% confidence interval and a 95% confidence interval under the t distribution, and what the ratio was in all of your guesses. And so most of you were right in that almost all of them have a 95% confidence interval that is larger than the 50% confidence interval, but there's not much of a difference. If this were coming from sampling, that ratio would be over 3, and none of you had a ratio between your 50 and 95% intervals that was that large, meaning that you were willing to go from 50% confident to 95% confident without making that interval very much larger. And that's not invalid. I mean, your intervals are based on, I don't know, life experience and not on random sampling. But just to say that relative to sampling, you're not increasing your interval very much to give much better odds. Maybe to put it another way, you know, this one here, they're saying I would bet even money on his age being between 51 and 61, but I would increase that to 19 to 1 odds. So bet $1, I give you $20 just by adding this extra couple of years. So when you put it that way, it's kind of implying that you know, you're giving away that extra confidence pretty easily in a lot of these cases. Just saying. I wonder actually if I had put it differently, if I had put it in terms of betting, if there would have been more of a difference between these. Like, what range would you put if you were betting even money and if you were giving 19 to 1 odds?
It would have been interesting to make it real money too.
Yeah.
That would have been very interesting.
Yeah. I guess this is one of the things that makes good gamblers is they're good at estimating odds like that and estimating their confidence in things and making accurate estimates of those odds. Okay, just quickly from what you covered last week, you remember how to calculate the margin of error, which is you calculate the margin of error, either it's 1.96 for a 95% confidence interval from the normal distribution, or you use the t distribution if you have estimated the standard deviation from a sample. And then the confidence interval is that the standard error times this critical value, this whole thing would be, this part would be 1.96 for the normal distribution. It's something usually a little bit larger than that if you're using the t-distribution, and this gives you your standard error, or sorry, your confidence interval. Just by way of example, going up to 22 degrees of freedom, the t-statistic at an alpha level, so a 95% confidence interval, alpha of 0.05 is 2.07. Let's see if we can actually see that here. Here's 22 degrees of freedom. And here at this column, one tail is 0.025, two tails is 0.05. It is 2.07. In this case, we had 13. It goes up to 2.16. So if there were no error from estimating the standard deviation, then the confidence interval the multiplying factor would be only 1.96, but because of that uncertainty in the standard deviation, it goes up to 2.16. So you should, by the time you're done your assignments and preparing for the exam, be pretty comfortable with calculating confidence intervals for proportion or for a mean using a normal or a t-distribution. Yes?
When do we use the one tail and the two tail?
You will only use two-tailed values for confidence intervals. Under specific, very specific tests, and I will talk about this for hypothesis testing, you may use a one-tailed distribution. You use a one-tailed distribution when you have a one-tailed hypothesis. For example, a null hypothesis that the mean is less than or equal to some value as opposed to just equal to, so that you could, if your null hypothesis is that the mean is less than or equal to that, then even if you have a very small value that is much less, such that it's well outside of your symmetric sampling distribution, you're still not going to reject the null hypothesis. Those are the cases where you would use the one-tailed probabilities. You're generally not going to use it. There are very few circumstances where it's actually appropriate to use. And so I generally don't have you do it because I don't want you getting in the habit of doing it. But it is important to know what it is and to know how you would use it. And we will cover examples, or at least an example of that. Thank you. All right, so the key points here are that you understand that relationship between sampling distributions and the confidence intervals, in that the confidence interval is based on the sampling distribution, and then you'd be able to estimate confidence intervals from data. With that, let's go on to hypothesis testing. Closely related to confidence intervals, but specifically when we want yes/no statements. And for example, the population mean is equal to some hypothesized value, or whether the means in two populations are different from each other. For example, if an intervention has some measurable effect relative to the control group. So it can relate to means and also to proportions. Say, do hypertensive smoking men have the same mean cholesterol level as the general population? Or does intermittent screening and treatment for malaria improve health and education of school children in a certain area? The example that I've posted this paper on this week's materials, just because it's a good example of a public health application of hypothesis testing, and they're everywhere. It's not hard to find. But in this example, the researchers are interested in the impact of screening and treatment for malaria intermittently on school children, on their health in terms of anemia and also outcomes in school. And in this cluster randomized trial, certain schools were continued with the standard of how things were being done, no change, and then an additional intervention was done in another set of schools. These outcomes were measured in the control schools and in the treatment schools, and compared against the null hypothesis that the treatment had no effect on these outcomes. And in fact, in their conclusion, they say in this setting in Kenya, IST, intermittent screening and treatment, is not effective in improving the health or education of school children, possibly because they give a couple of reasons, but the take-home message is that we did not see evidence that this was in fact effective in improving these health or educational outcomes. Yes or no? So the logic of what we're doing is that we have a set of observations from a sample, okay? And this comes from one of two possible distributions of the population. One being a usual distribution, what we're accustomed to seeing, what there is and no change, and an alternative being that it is from some new distribution that is not the same as what we're expecting or what we've seen in the past. With a classic statistical teaching example of one sample inference being, got a handful of beans, only a few of them are white. I've got a big bag of beans here and most of them are white. Probably then this handful of beans is not from this bag. Simple, right? If your handful of beans looks very different from that big sack of beans, then it probably came from somewhere else. Another nice analogy, the courtroom trial, which is good for its discussion of evidence. And the analogy of the courtroom trial is that we have a defendant who is accused of a crime, but they are guilty, or they are innocent until proven guilty. So in the absence of any evidence, we assume that they are innocent, and that is our null hypothesis. What in the absence of any countervailing evidence, we will assume to be true. That's what the null hypothesis is. Then you have the prosecutor, the investigator, who tries to prove the guilt of the defendant, and they have to do that based on evidence that is contradictory to that null hypothesis. And that alternative hypothesis is only accepted when there is abundant evidence to reject the null hypothesis, or the way it's supposed to work. And under this example, this is a nice little table to help you keep in mind these possible outcomes of hypothesis testing. So there are two things. There is the truth, something that we don't actually know, or we probably wouldn't be bothering to do a study, but we have a null hypothesis and an alternative hypothesis, and they are formulated in a way that they're exclusive. Only one or the other can be true, but one of them has to be true. Either H0 is true or H1 is true. So thinking back to that probability stuff, these are mutually exclusive and they are exhaustive. So they can't both be true, but one of the two has to be true. So either guilty or innocent, either this this handful of beans was from that bag or it wasn't. There's only two possibilities. And so if the null hypothesis is true and we accept that null hypothesis, it's the right decision and it's an acquittal. If the alternative is true, the defendant is truly guilty and we reject the null and convict, that is also the correct decision. But there are two types of error. We can make the error of a wrongful conviction. That is a type 1 error, and that's the type of error that we will control for in hypothesis tests. That is the kind, like with a trial, is generally considered the worst kind of error to make and the one that we have to be most cautious about protecting against. That said, we can also make the mistake of the alternative being true and failing to reject it. That is a type 2 error. So that would be allowing the guilty defendant to go free, or not noticing that they're not noticing the evidence of some true difference. That's a type 2 error, and that is where power analysis comes in, something that we plan for in advance of experiments. There is analogy between confidence intervals and hypothesis testing in certain cases. You have to be careful about how you apply it, but in the one sample tests, it is easy to do, and it is possible in other cases as well. But the basic logic is this: if you set a 95% confidence interval around your best guess, and your null hypothesis lies outside of that confidence interval, then you would reject the null hypothesis and accept an alternative hypothesis because your data, your observations are inconsistent with that null hypothesis. So just to close that, if in the case of if we had the null hypothesis being a certain age, and that and our confidence interval includes that age, then there is no evidence to reject the null hypothesis. It doesn't mean that the null hypothesis is true, it just means we don't have enough evidence to be able to reject it. Although hypothesis testing is pretty easy to do with software, I'm going to teach you to do it through a number of formalized steps, several of which don't include software at all, but just understanding the hypothesis that you're testing. And I'm going to send you through these 5 steps here just as a way of being clear about the test you're doing. So the first step is to just state your hypotheses, including your null and your alternative hypotheses. And I'll give you some examples of these, but it's going to be written out in most cases as a formula. Second, you'll specify your significance level. That is the probability of type 1 error that you are willing to commit. So the most common value by far is 0.05. This means that you want to limit your probability of the type 1 error rejecting the null when the null is true at 5%. Third is to actually collect your observations, do the experiments, get your sample, and compute the test statistic. And in the case of a mean, you will use the normal distribution to calculate your test statistic, and it will be part of a t-sampling distribution if you have to estimate the standard deviation. But in all kinds of hypothesis testing, at after you have your sample, the step is to calculate the test statistic. And based on that statistic, you calculate a p-value, which is just your probability of observing that test statistic, or something more extreme than it if your null hypothesis is true. So you'll have what's called a null distribution that is what the distribution of this test statistic would be if your null hypothesis is true, and then you calculate its probability under that null distribution. Finally, you compare that p-value, that probability, to your significance level alpha and decide whether or not to reject the null hypothesis and state that in terms of the subject matter. So the null hypothesis is always your hypothesis of no difference. So this is somewhat different than not all hypotheses are null hypotheses. You might start, your malaria study having the hypothesis that this intervention is going to improve educational outcomes, but that's not a null hypothesis. And in fact, even if your own hypothesis is that there will be an improvement, you're not going to use a one-sided null hypothesis that the outcome is going to be the same or worse. Your null hypothesis will be one of equality, that there is no different from the usual standard of care and this new treatment. Does that make sense what the null hypothesis is? It's the hypothesis of no difference.
What were you distinguishing it from?
I was distinguishing a null hypothesis from a scientific hypothesis, or like a public health policy hypothesis, that the hypothesis that doing intermittent screening and testing will lead to an improvement in health outcomes. So that is a hypothesis, but it's not a null hypothesis.
But your null hypothesis in that case would be like doing those screenings, whatever, does not change whatever it is, right?
Yes.
It's like the anti-hypothesis.
That's right. It's like it's your anti-hypothesis. That's a good way to put it. Your null hypothesis there would be that the intermittent screening and screening and treatment has no effect on these outcomes. And notice that the null hypothesis there was not something with an inequality, not that it will have no effect or a worsening effect. It would be hard to justify including a worsening effect under your null hypothesis. And then the alternative hypothesis includes everything that is not included in your null hypothesis. And it states that there is a difference between your observed population and the null hypothesized population. And this maybe is a little bit vague here, saying the distribution of the observed data, because we're not talking about the actual observed data. We're talking about the population from which it came. So these hypotheses are about the whole population. There are hypotheses that we cannot observe directly. They're not, our data are not the whole population. The hypotheses that are about the population are samples, or our data include only a sample of that population. So if the alternative hypothesis is true, then hopefully the data that we observe, the sample that we draw, will look like something inconsistent with that null hypothesis, something that would be too unlikely to happen from chance variation, if the null hypothesis were true. And so if that's the case and the data we observe seem very unlikely, we will accept the alternative hypothesis. So here are a couple of explicit examples of the null and alternative hypotheses. For a one sample test on the means, the null hypothesis would be that the mean of our study population is equal to this hypothesized mu0. So this is something specified in advance, and the alternative is just that they are not equal. So for example, if the blood pressure in the general population is 211 milligrams per 100 ml, then, and we are looking at just a population of smoking males, then our null hypothesis would be that the mean blood pressure in this study population is equal to that in the entire population. An alternative would be that they are not equal. Make sense? For two samples, then instead of that mu0, we actually have two different populations here, mu1 and mu2. And the null hypothesis is that the means in those two populations are equal. And the alternative is that they are not equal, or equivalently, that the difference between the two is 0. Either of these are valid ways to write out your alternative hypothesis. But in all cases, I'm writing H0, HA, a colon, and then an equation with an equality and an equation with an inequality. And an example, yeah?
Shouldn't the alternative hypothesis after the or, shouldn't it be not 0?
Oh yes, sorry, that is a mistake. This should be not equal to 0. Good catch. Let's see if I can fix this here. Pointer, pen. There. Yes.
Is mu the right symbol here if it's two samples?
Yep.
Because if it's two samples, you wouldn't use X bar?
So the hypotheses are about the population.
Okay, so the population is represented by each of the samples.
Right. Yeah, that's an important distinction, that the hypotheses are about the populations, not about your sample. Because of course, if you were to calculate the difference x1 bar minus x2 bar, it's never going to be exactly 0. There's always going to be a little bit of difference by chance between them. So if you're just talking about the samples, your null hypothesis would never be true. But it is a plausible hypothesis for the population. If you have an ineffective intervention, then the difference between a control and the intervention will be 0. Or I guess in some cases it could actually be a harmful intervention. So in that clinical trial example, there were two populations. There was the population receiving the placebo, the business as usual treatment, and the population receiving the new treatment, with the null hypothesis that the prevalence, well, one of the outcomes being anemia, that the prevalence of anemia in the control and the treatment populations are the same, alternative that they're different. So it is also possible to specify a one-sided alternative, and sometimes this can be tempting to do when you have a strong feeling about what the direction of effect of a treatment should be. So I'll tell you, In this case, the null hypothesis is actually an inequality. It includes the equals still, so mu less than or equal to mu 0, or it could be greater than or equal to, and the alternative is the other with two samples, the same thing. It's an inequality with the equality under the null, and the opposite for the alternative. And that choice between the one-sided and the two-sided test depends on the context of the problem, but it is controversial and very rare to use the one-sided test because it affects your p-values. And specifically, the one-sided test, if the directionality is correct, gives you a p-value that's only half as big, because you consider that you don't even count the probability in that other side of the test. So if you you remember the shape of the normal distribution, above and below 1.96, there's 2.5% in each of those tails. So if your null hypothesis is true, then above and below 1.96, you'll get a sample line in there 5% of the time, but you'll only get it in one of those tails 2.5% of the time. So in general, your p-value will be half as big with a two-sided test if your directionality is correct. So if your mean 1 is greater than your mean 2, then the p-value would be half as big. If it's in the other direction, then that's not the case with the p-value. So two-sided tests are the norm, and you should almost always use them unless it is clearly justified in advance of the test and there is no reasonable possibility of another alternative hypothesis. So be careful. I don't recommend the two-sided tests in almost any circumstances. So step 2, just choose your alpha, probably 0.05, but it could be other things depending on how stringently you have to control your type 1 error rate. And note in here that this probability of making an error is based only on sampling variability for a single test on your sample. As soon as you start doing more and more hypotheses, then they can compound and increase your overall type 1 error rate. And it, of course, does not include other kinds of error like biases, like experimental design problems. It's just sampling variation. So when you're calculating the test statistic, it is always something that has a small value when when what you observe is close to what you expected, and gets more extreme, either larger or sometimes more negative, if the more unexpected your data is. Like the further your mean is from what you hypothesized under the null, the further that proportion is, or other things. But this is the general property of test statistics, is that they increase in size as your sample is more inconsistent with the null hypothesis. And here is how you calculate it for the one sample z-test. It is just the mean of your sample minus the mean under the null hypothesis divided by the standard error. And it's calculated in that same way for a t-test, except with this sigma being in S. In practice, we almost always use the t-statistic just because we don't have the population standard deviation. We're estimating it from a sample. What this looks like is you have some kind of probability distribution, which is the distribution of your statistic under that null hypothesis, and you place your sample somewhere on this distribution. Let's say it's right there, and then you calculate, using this distribution, the probability of getting what you got or something greater than it. And under a two-tailed test, also something more extreme on the other side of the distribution. And you add those probabilities together, and that's your p-value. This drawing is, I think, a little bit misleading because this would be your p-value for a one-tailed test or a one-sided test. Under the two-sided test, you have to include two tails, two sides, like this. Yes.
So you have to know for sure that you're not ignoring things that are important when you pick a one-tailed test. Like with the intervention, you have to know it's not going to make it worse, right? Because then if it does, you wouldn't have that in your model. Or whatever the threshold.
Yeah. Even if you knew your intervention couldn't make things worse, it would still be problematic to use if you use the one-tailed test, it means that if you have, for one thing, if you have an extreme sample on that worsening side, you would not reject the null hypothesis. So it means that there is no possibility that you're in any universe where this treatment could make something worse. So, that's something that's hard to say and be absolutely certain about. The one case that I know of, maybe Tony knows of others, but where one-tailed hypotheses really are commonly used is in drug equivalence trials, where you have a standard drug used to treat something. You already know it works. You have some new alternative that maybe is cheaper to make, and all you want to know is that it isn't worse. You don't expect it to be better. You just want to know that it isn't worse. And in there, it has to do with like your interest that you are going to you're going to reject your null hypothesis if it is worse. But if it is equivalent or better, then that's just all fine. That's all under your null hypothesis of business as usual. And so it actually makes sense, and it makes your test then more sensitive to a worse alternative. Good. Okay, a lot of text here, but step 4, as we showed, is to calculate the p-value based on that assumed known null hypothesis, which is just your probability of observing what you saw or something more extreme. Notice I always say or something more extreme because your probability of getting exactly this mean is infinitesimal and not relevant. What's relevant is observing what you got or something even more far out than what you saw. And finally, you accept or reject your null hypothesis. And the smaller the p-value, the greater the evidence against that null hypothesis, at least in terms of sampling variation. And the threshold is the alpha that we set in step 1. If that p-value goes below alpha, then we're going to reject the null hypothesis and accept the alternative. Otherwise, we say we don't have evidence to reject the alternative, so we're just going to stick with the null hypothesis. Doesn't mean that we've proven the null hypothesis, it means we've failed to disprove it. So looking back at this, this example that we have, let's see, what is the outcome variable? Well, there are several outcome variables here. Let's see, there was, and they stated it, the primary outcomes were anemia and sustained attention. Secondary outcomes were malaria, parasitemia, and educational achievement. Okay. And by the way, are these means or proportions that we're doing tests on here? Let's see, they say during the intervention period, an average of 88.3% of children in schools were screened at each round. 80% of children in the control and 80 in the intervention group were followed up. No impact of malaria IST intervention was observed for prevalence of anemia, an adjusted risk ratio of 1.03, confidence interval 0.93 to 1.13, P of 0.621, or on prevalence of P. falciparum infection. So those two, are those prevalent, or are those binary or continuous? And are these proportions or means?
Binary proportions.
Yeah, binary proportions. This one, then there's this other one, scores of classroom attention. That one's probably continuous, and we're talking about means. So we've got both kinds of tests in here. Let's see, what is the significance level alpha? They don't explicitly say it, but based on the fact that these are 95% confidence intervals, I'm going to say that the significance level alpha was 0.05. Here's the p-value. And was H0 rejected? No, H0 wasn't rejected. And I didn't actually include on here how this result was reported, but you saw that already. So even if a paper is using statistical methods that you're not familiar with, such as a cluster randomized trial, which is a little bit complicated to analyze because you have clusters of schools and then students sampled from within those schools, you can still interpret the findings and interpret those results based on just your essential knowledge of hypothesis testing, which is great, right?
Is that based? Is that based on like the English here, the fact that there was no impact? Is that what that's how we? I'm just like in epidemiology we learned, so like a risk ratio of 1.0 means that there's no difference. So because the confidence interval includes that score.
So based on both of these things, so the confidence interval includes an adjusted risk ratio of 1, and the p-value is 0.621. So both of those are saying that there is no good evidence against the null hypothesis of an ineffective intervention. Yeah. Okay, back to our fun data set, and I also asked you to guess my age, and I didn't give away Tony's age, but I'm giving away my age.
Well, you never know the mean, never really know the mean of the population, so it should be.
That's right.
I'll just say that I was very pleased with the survey.
Good. Well, and actually that is a good point to make, that if people did know your age, then the whole exercise is pointless. That the exercise of putting a confidence interval would be nothing. And actually that was part of why the last 2 years, I give away my age, but not Tony's, so as not to ruin the exercise. In case, I don't know, in case word gets around.
I'm sure.
So my true age is about 42.9 years. And so I'm going to use that as the null hypothesis. If I act my age, then that is the mean age. That should be the mean of people's guesses over a large enough number of guesses. So I'm going to write this out as my null hypothesis. Set an alpha level of 0.05. Calculate this test statistic based on the sample mean. So the mean age of guessing was 40.6 years minus my actual age divided by the standard error, which is the standard deviation of 4.3 years divided by square root of the sample size 13, and that gives me a t-statistic of minus 1.92. And it really does. I did this with a calculator this afternoon. So it's not exactly my age, of course, but is it consistent with sampling variation? It's one thing to write this out as this null hypothesis as a formula, which we want to do, but what does it really mean here? What is what is mu? It's a population mean. A population mean of what? What is it?
Our guesses.
Population mean of estimates. So yeah, it would be like if I'm going to say if I consider you to be a sample of all the students in the school, or a sample of the whole world. If I assume that you're a random, unbiased sample, that would be a stretch. If it were the whole world, it's probably not too much of a stretch if we were to just look within the school, at least in terms of your age guessing tendencies. Then this mu would be the average age that people guess that I am. And the null hypothesis being that it's equal to my true age. So what do I get? Let's do it using the table here. What is the critical t? Let's see. This is out of the back of your book. Table B, we have 13 minus 1 is 12 degrees of freedom. And we want this two-tailed 0.05, so we go down there to 12, and the critical value is, there we are, 2.18. So compared to what we observed, 1.92, cover this part up. What do you think? Is that evidence to reject the null hypothesis of the mean population age being equal to my true age? This is the critical t, and this is what we observed. Are we going to reject?
Yeah.
No. We're not going to reject because the value of t we observed is not any more extreme than what we expect under the null hypothesis. So under the null hypothesis, where the mean guess is equal to my guess with the standard deviation that we estimated, if we go between t equals minus 2.18 and 2.18, it looks like this, and there's a probability of 5% in these two tails. So the sample that we took falls within this white region in the middle, consistent with the null hypothesis. And this is actually a good example of where if we had picked a one-tailed t-test, this is a small enough difference that we could have ended up with a statistically significant result if for some reason we were doing a one-tailed hypothesis test. Alternatively, with the software, just doing a t-test here and specifying what the mean is under the null hypothesis. You can do this also by subtracting 42.9 from all of the values, but I just specified it. It calculated the same value of t minus 1.92, told us 12 degrees of freedom, and gave us a p-value of 0.079. We could have estimated that p-value. Well, no, we can't really estimate that p-value from this chart. You have to have some, once you're dealing with the t-distribution, you need software to actually get a p-value. Best you can do is get your critical value and compare to that if you're using the table. The 95% confidence interval, which I didn't calculate by hand this time, was between 38 and 43 years old. So it just barely contains my true age. So finally, in step 5, we're going to accept the null hypothesis that I do not act significantly different from my age. I don't know if I'm happy about that or not. It was a small sample size, so. So although the average was a little bit younger than my age, 2.3 years, with the sample size that we had, that was consistent with sampling variation. And if we were to take another sample of the same size, we could very well end up seeing a mean equal to my age or even greater than my age. It's getting a little bit late, so I think I might go ahead and breeze through this cholesterol test. It is just the same steps here, laying these out. It's good to take a look at these and be familiar with these steps, because they will ensure, when I am going to, on the test, try to make sure that you understand the meaning of the hypothesis testing. I'm not just going to be having you go through and calculate p-values and report them. I'm going to really try to probe and make sure that you understand what the null hypothesis is, what the alternative is, what they mean, and what the interpretation of various results are. And I know that probably coming into this, there was confusion about confidence intervals. There was confusion about what a p-value is in terms of type 1 and type 2 error. There are a lot of ways to be confused. So yes, more examples. I just want to make this note on testing proportions that that, as I noted before, you can think of testing proportions as in the same way as you would have for continuous data, but using a value of 0 for no event and a value of 1 for an event, so that the mean is a proportion. And then under the normal approximation to the binomial distribution, your standard error is given by this equation, and you can proceed in the same way as for continuous variables and for means. Recall, as I mentioned, that equivalence between hypothesis tests and confidence intervals, that you can use confidence intervals to do a hypothesis test if the confidence interval is consistent with your hypothesized mean or difference in means. It is simple for the 1 sample test that we do this week. It is more complicated for 2 sample tests, which we're not going to get to until next week. But just remember that nice intuitive equivalence that you can reject the null hypothesis if your hypothesized mean falls outside of the interval. It's a little bit trickier for 2 sample tests, in that it will be a confidence interval on the difference in means, not confidence intervals for each of the means. We have to explicitly draw a confidence interval on the difference, but we'll worry about that next week. But the key thing is the second point. When we do two samples tests, just because you have overlapping confidence intervals on the means from each of the samples, that does not preclude rejecting H0. You might still reject H0 in that case. I think I might, it's getting awfully late here, but we're almost done. I just want to point out here, I showed you this slide before on the one with the example of the courtroom trial, but under the but I just wanted to add to this, so there's the type 1 error, which is when you fail to reject, or sorry, when you reject the null, but it was true. The type 2 error, when you fail to reject when you should have. And then this other corner here of no error is your power. That means that the alternative is true and you accept the alternative. That's the power of your test. It's sort of its sensitivity. It's your ability to detect some true difference. And you will learn a little bit more about power next class. But some basic ideas of it are that there's a trade-off between your type 1 error and your power. So that type 2 error, which is failing to reject when you should have reject, that will go down, and since it's 1 minus your power increases as your true difference in means gets bigger. So the bigger a difference there is, the easier it is to observe, the better your power. That type 2 error goes down again if your variability decreases. So for the same difference in means, if there's less sampling variability or less variability in the population, again, it becomes easier to distinguish between those means. And that can happen either because there's less variability in the population or your sample size increases. Either of those will decrease your standard error. The type 1 error, of course, is just fixed because we set that at the very start. And it does, of course, affect the power in that the smaller we make alpha, what is that going to do to the power? So you want to have a very, very small alpha, have very high confidence if you do reject the null hypothesis. What is that going to do to your power? Higher power. Why higher power?
The confidence is large, and then
so by selecting a very, very tiny alpha, you're making it more difficult to reject the null hypothesis. You need a lot of evidence to reject the null hypothesis. Mm-hmm.
Would that cause so you decrease, if you increase the alpha, that means you decrease.
What do you mean?
Sorry.
What do you mean by increase alpha?
If your alpha is getting smaller and smaller, that means you'll make less type 1 errors, but in return you will make more type 2 errors because now it's going to be harder to reject the null hypothesis.
Yeah, and so your power will decrease because you're making more type 2 errors. So you're saying that the difference must be very, very obvious. And so it will be easier to make that type 2 error. You will fail to reject the null hypothesis, even if the alternative is true, because you don't have enough evidence. So in the analogy of the courtroom trial, it's just sliding that bar, saying, if you need stronger evidence to convict, then you're less likely to convict, and you're then more likely to you have less power to convict because you require more evidence. So in general, we want a high power. This is something that you plan for in a study in sample size and power calculation. And whereas the alpha, the type 1 error rate, protects us from spurious results, type 2, or the power, protects us from wasting money on a sample that really has very little chance of observing a difference anyways. But we'll get back to that. And I'm going to wrap up today. We'll go back and review a little bit of this stuff at the end and turn it over to you, Tony.
Okay, take 10 minutes and we'll get set up.